Okay, hello and welcome to this session. Sorry for the glitches. Yeah, the main issue is that I am here from Italy, and we have my colleague Matheus that is connected from Brazil. So this explains a bit of the technical glitches we had at the beginning. This session is going to be about the usage of .NET on devices. We call it .NET at the edge. Few months ago, the more popular way to define this was IoT. Now we talk about edge devices. I am Valter. I'm from Toradex. I've been working on embedded and IoT devices for many years. I used to be a Microsoft MVP until last year, working mostly on low-level drivers and devices. And we also have Matheus connected. Can you hear me?
Hi guys. Yeah,
okay.
You are hear me?
Okay, yeah. So now you can introduce yourself.
The image is a bit lazy, right? But I hope you are hear me well. So I'm Matheus Castello. I'm from Brazil. I work with Valter at Toradex. We are working in the Horizon team. I work with him in the Visual Studio and Visual Studio Code extensions for the Toradex hardware, and we will show something from this on this session.
Yeah. First of all, we thank our sponsors that make this conference possible. And then let's move into the real content. So let's start with some kind of background history. Here we say .NET Loft devices. Actually, in this session, we are going to talk about using .NET Core or .NET 5 on devices. I just learned today that .NET 5 is the right definition. But the story of .NET on devices starts in 2002. So basically, .NET on devices can even get a driving license nowadays. It started with two different projects. The most famous one is the one on the right on your screen. That is Windows CE. Windows CE has been Microsoft operating system for devices until a few years ago. In 2013, they released the last version, and it's going to be the last, not the latest. They are not going to develop it anymore. Version 4 of Windows CE in 2002 was actually called Windows CE .NET. And the idea of adding .NET was really to show that this small operating system running on small devices could run the .NET framework that was Microsoft's brand new flagship product at that time. They added the .NET suffix to the OS, then they removed it because it was generating some confusion. Some people were thinking that you could only use .NET to develop there. It was not true, but it remains there until now, basically. Another less known project is Project Spot, and there you see a coffee machine running it. Actually, a bit more famous implementation of Project Spot are those watches. Spot was what then became the .NET Micro framework. Basically, it was designed to run on even smaller devices, usually powered by a microcontroller, providing a small subset of the full-blown .NET framework. But we are talking about 2004. So it's still 16 years ago. And if you think about what was the most popular smartphone in 2004, you see this Motorola Razr 3. That, I mean, at that time was quite a good smartphone, but nowadays we don't even consider it a smartphone anymore. It's just a feature phone. It could send messages, it has a camera, but not more than this. And at that time, we already had .NET on devices. Also in 2004, this guy made the most popular song of the year. The guy is named Usher, and the song was named Yeah. The guy also made 3 out of the most popular 20 songs, but honestly, I don't remember anything about this guy. But on the other side, we still remember something about .NET. It's still there. But let's change the perspective a little bit. We say that .NET loves the devices, but do the devices love .NET? That's a good question. We have different implementations of the .NET framework on devices. We start with the micro framework. As we say, it used to be a small implementation from microcontrollers. It was born as Pod, then became the .NET Micro Framework, but actually is no longer supported by Microsoft. There are still people using some devices. I think Matheus had a good sample of these kind of devices. Running even the .NET Standard Framework now. But the .NET Micro Framework really never reached fully the market. There were those watches in 2004, but then I think no more commercial products using it. And over time, what was quite a dynamic and thriving community kind of disappeared. There were some companies supporting it, GHI and also Mountaineer, but they are no longer working on this kind of architecture. We had the .NET Compact framework. This one has been around for many years. There are many products using it. It has been ported also on Windows Mobile. If you have this kind of application in shops or restaurants where you make an order from the terminal and is sent back to the kitchen or whatever, it's quite often developed using .NET Compact framework. It provided database engine, a way to design your user interface. It was quite a good experience on those devices at the time. But as I said, Windows CE development stopped basically in 2013. Microsoft is still supporting the operating system, releasing patches up to 2023. It's going to sell it in license up to 2028, but there is no major development around this architecture, and the features of .NET Compact Framework are stuck around .NET 3. Is even lacking some of those features. The UI is only Windows Forms and so on. We also have Universal Windows Platform. This runs on Windows 10 and of course also Windows 10 IoT Core. But again, to be honest, Windows 10 IoT Core didn't get much traction on the market compared to what was even Windows CE. There are some devices out there. You can run Windows 10 IoT Core on the Raspberry Pi, I think up to Raspberry Pi 3. But again, it never really reached big numbers out there in the market. So, okay, we say .NET loves devices. Devices are not loving .NET so much, but we have .NET Core. And .NET Core is definitely quite interesting and very popular on devices.
Hey, Valter.
Yeah.
I sent on the chat the link for the Wilderness Lab Middle App 7. That is hardware that runs .NET Standard 2. Right?
Yeah.
So,
yeah, that's pretty cool because here you don't even have a micro version. You have .NET Standard, of course, with some limitations, but you can run it on a device. But again, this is a cool project, but it's definitely not a device that got large numbers on the market, as the two we see here, the Arduino and the Raspberry Pi. So when we talk about running .NET on devices and specifically .NET Core, we should think about which kind of devices we are talking about. And you see those two big categories. One is the Arduino. That means basically devices that are based on a microcontroller. Here we run a firmware, so basically not a full-blown operating system, and usually memory and storage are measured in kilobytes. I know that for some of the people in the audience, maybe kilobytes sounds strange, but it used to be a unit of measurement for memory and storage capacity until a few years ago. It's still the unit we use on microcontrollers. But we have also embedded devices that are not so small. If you think about the Raspberry Pi, there you have an application processor. That means that can run a full-blown operating system, usually Linux nowadays. And here we have memory and storage, and usually we are talking about megabytes, if not gigabytes. So if you are talking about the very small devices, there are no chances of running .NET Core. If you want to see, there are some experiments around .NET Standard. If we are talking about the class of devices that provides more or less the same feature of a Raspberry Pi, then definitely here we can run .NET Core. What we need to balance when we think about it. On one side, we can develop some native software. When we develop native software, we don't need the runtime. So we can generate an executable file that is fast and small. On the other side, developing this kind of software, it's a bit more complex. We need to set up a complex tool chain. We need to cross-compile. We need also to take care of all the memory allocations from our software and probably write some low-level code. On the other side, if we think about managed software, managed is the term we use for .NET, but applies also for other kind of languages. There we definitely need the runtime to run our software. We have an executable file that is definitely much bigger. Maybe the executable itself is not so big, but we should include the runtime in the comparison. But on the other side, we have a very fast and very productive development model. So here's the point is, to net or not to net? Of course, depends on your scenario. If you are designing a device that needs to be produced in millions of devices, then probably you need to save any penny you can save on the bill of material, means on the hardware components you buy to create your device, because every euro or dollar or whatever you save is going to be multiplied by 1 million. So it's definitely some saving. Even if I'm spending a bit more time in development, because development is a bit more complicated, okay, this is justified by the savings at the end. But on the other side, if we think about a typical industrial medical device that is usually sold in hundreds or thousands of units, saving a few euro on the bill of material probably doesn't make sense. If I'm saving 3 euros on a device that costs 300,000 euros and that I'm going to sell in maybe 20 pieces, and to do this, I'm spending 6 months more in development. I'm actually not saving any money. So on this kind of devices, probably it makes sense to use some tools, some frameworks, some development environment like .NET that help me be more productive rather than optimizing the usage of my resources. Okay, so when we are talking about hardware, we should also think that hardware is getting more and more cheap. If we think about Raspberry Pi itself, if we think about the Raspberry Pi itself, we should think that we are talking about a device that used to cost $35 in 2012. But let's see what and it's still costing around $35 nowadays. But look at what the Raspberry Pi is providing. If we look at the Raspberry Pi in 2012, that means just 8 years ago, so not that far away. This device was providing just a single core CPU at 700 megahertz. It was providing 512 megabytes of RAM. This is the megabytes we have been talking before. If we look at the Raspberry Pi nowadays, version 4, that has been released last year, it's providing 4 times more CPUs, more cores to be correct. And those cores are running at more than double the speed. And we also have 4 times the memory at the same price. So if you are evaluating your project over time, consider also that the hardware you use to start your project nowadays, if you release your software in 1 year, it's going to be cheaper than what it is nowadays. And this is where .NET Core really shines. We can run it on Linux. We can run on ARM 32 and 64-bit architectures. It has a very big community around it. .NET Core runs on ARM also because its roots are in ARM devices, on Windows CE, on the micro framework. We have very good development environments. We can use Visual Studio, we can use Visual Studio Code, and all the system is designed to be small and efficient. Because the idea here is to try to reduce resource usage. And you can say, okay, but this is a system that is designed for the cloud, for servers. Why should I care about saving resources in the cloud or on the server? It's still quite an issue, because if you think about this, let's think about Microsoft. Microsoft wants to run services in the cloud, and .NET is definitely one of the platforms. If Microsoft is able to run 100 services, .NET services on a single physical machine, that is pretty good for them. But if they can save some resources and run 200, they are going to get double the money. Okay, so that's a good reason why, even if the system is designed to run in the cloud, the system, the Microsoft is investing a lot of resources in keeping it efficient and very small. So what are the challenges if we want to create a .NET application for a device? Of course, we still have to deal with some kind of reduced footprint. We talk about the Raspberry Pi 4, it's 2 GB of RAM, is definitely quite some memory for an embedded device. But if we compare it to your desktop machine, probably it's not that much. So we need to write our software taking care of some limitations. We need to deal with connectivity. Embedded edge devices are not always connected. They may be in some remote location, they may use cellular network, connectivity may be not very fast and may sometimes even expensive. So if you have to deal with network protocols and so on, maybe you need to evaluate the choice of protocols to reduce bandwidth or to use something that is quite efficient. And the last point is embedded means integrating hardware and software. And so probably at some point I need to access my hardware. And hardware access is definitely an important point. But about this, we are going to see a live coding session by Matheus after my demo. And talking about the demo, we are ready to start it. I just took an existing sample. It's a Blazor sample from Alejandro Lozano. And basically, it's just a dungeon game that it's implemented in Blazor server side. So basically, it's using mostly the server machine. Yeah, thank you for yeah. I know that the webcam has been frozen, but we had some issues. We are connected with Skype and the Skype connection dropped. So that's the issue. I couldn't reactivate it during the talk. But yeah, you just see my face in the corner. Sorry for this, but I hope that the rest of the demo it's quite useful anyway. So I was saying this is a demo using Blazor server side. So it's performing most of the operation on the server, and this means on the device. I have the application here in Visual Studio Code. I'm not going to go through the code. I'm honestly not a Blazor developer myself, but you can find the link in the slides. You can look at it. What I wanted to show you is that now this application is running on an embedded device. Is a NXP IMX8. It's a device from Toratex, of course, our company. Is the easiest for me. It's running inside the Docker container. So we have Docker, .NET runtime, and my application. And let's see if it works. I have my browser here. Oops, just let me copy the name of the machine. So I'm not going to make any spelling mistake. Okay, let's do it. Okay. Now my browser is not super fast because of course I'm also broadcasting with Teams, but here it is. We have this very simple application, but it's simple, but it's anyway already leveraging some features of .NET. And you can see, okay, game over immediately. I'm super lucky this time. Let's see if I can restart the game. Okay. I have this orange guy in the corner and I can move it around. Okay, it's not probably the best usage of server-side technology, but was just to show you how you can take an existing .NET application and run it on a device. Now I'm switching to Matheus. I hope that Alessio is here. If Matheus can share his own webcam, we can switch for the presentation. And sorry for the glitches at the beginning.
Okay. My camera is already being shared. You are seeing my screen. Cool. Thanks, Alessio. Now you are seeing my Visual Studio Code, right? With some C#9 code. Okay. So as Valter said, we can run .NET Core on device at the edge, right? And it's common from on device, right? When we have an IoT application, access this hardware, access the general pin input output pins on this hardware to connect, attach sensors, get these reads from the sensor and send to the cloud, to Azure, or make some connection with the IoT hub and this kind of stuff. But with the .NET Core, with the .NET 5, we have two ways to access this hardware or ask the kernel, ask the operation system and to access this hardware, right? We have the interrupts, the marshalling, and all this good stuff on the .NET to ask native code to do the things, right? But you have to write this, right? You have to make the bindings from the codes on the native methods, on native functions in the C# interrupt, right? And for this, we already have some project on inside the .NET project. Okay. You are seeing my screen yet? I see a green screen here. Only confirm for me if you are seeing me yet. So yes, okay. So I have here the .NET, the GitHub from the .NET project, right? And inside the .NET project, we have this repository here, the IoT repository, right? And inside the IoT, the .NET IoT repository, we already have implementations of these interrupts, right? And it is cross-platform. You can access the GPIOs in the Windows IoT, for example, and also on Linux. I will show here the demos running on Linux using these libraries to access the hardware. So first of all, let me show you guys that I have to use here the system runtime interrupt services. I want to show you that I running in the board, right, in the or target device. I want to show the OS architecture. First of all, I want to bring to here for you the CPU architecture that the .NET is running, and also let's show here the runtime information about the operation system that I'm running on my device. Let me show here also Tboard, right? I have this Toradex Apolis INX8 is a ARM 64-bit processor, right? This guy is a beast, have 6 cores, right? It's ARM 64 bits, 6 cores, right? And here we have some kind of hardware connected on the general input-output for our use, right? We have here an LED, a blue LED, button, and also a OLED screen, right? And we will use the .NET IoT with .NET 5 and C#9 to connect this. First, let me show here that we are running on the device. Valter already showed the Blazor application running on the device. also you use the extension here, the Toradex extension. If you go here on the extensions on VS Code, you can go and type Horizon and you find out here the Toradex Horizon support. We have support for Raspberry Pis also. So you can use Raspberry Pis to evaluate here our extensions. So what we have here, I have a .NET console application that the extension creates for me. And with a simple F5, I'm pressing F5 on my keyboard, and this will compile the .NET console application here. And also this will connect and make the sync, right, with the .NET binaries on the device, on the target. So starting, and we have, I put a breakpoint here on this line, and you can see that I'm running on the device, and this is making a remote debugging for me. If I press F5 again here, I can go step by step, and this is running on the device. This is very cool. I have here the hello world already printed. Let me clean up here the debug console. Let's go to the next instruction. Let's see the OS architecture. You can see that I'm running on ARM 64-bit. I can prove you, because if I go here on my terminal, I can go and run the .NET run on project, and this will run on my development PC. And on my development PC, I expect to see a Intel X64 processor running on my Microsoft Windows, right? But on the target device, and when where I connected on the remote debug, I'm running an ARM 64-bit and also a Linux operation system. Cool. This runtime information is cool to use when we have some cross-architecture or cross-platform application, and we have some parts of code or something that we can test and run only on this architecture or on this system, right? But let's do here the access to the GPIOs, the general input-output pins. And first I have to add here the package, right? I have to do a .NET add package system device GPIO. This is the namespace. This is the NuGet package to you have access to the .NET basis, .NET IoT basics class. Okay, so if I use here now using system device, you can see that I have inside the system device the GPIO, the I2C, the PWN, and SPI. So I can use all these basic protocols, right? Let's say to access our hardware, right? And we have this inside .NET already implemented inside the .NET IoT project. So for access to GPIO, I need a GPIO controller. Let's instantiate a new GPIO controller. And now that I have the controller, I can do the methods. I can do the things here to set up my hardware, right? First of all, I have to set up the pin that we will drive the LEDs. Okay, so I will open here the pin. Let me check which pin is connected. My LED is the pin 20, right? And also I have to set up here the pin mode. If I want to put or turn on or turn off, put the output is pin or make an input, a read, right? So this is a LED. I want to set up this for output, okay? And let's begin tipping with pin 20 to pin value low. So what I done, I set up the pin and also I already writing energy. I'm already outputting on the pin the value low, right? And now let's make the blink. Very Arduino-like. Let's do an infinite loop here. Let's use the controller to write the state of pin 20, pin value high. Also, I use here the system threading because I want to sleep.
Yeah, sorry, and a point is pin numbers and this kind of information. Usually, you need to get them from datasheets. So even if we are doing high-level developments, at some point we need to deal with the hardware. So we need to do what the hardware guys do and go read some documentation and some information there. But usually it's not that hard to find this information.
Yeah. So the LED is connected on pin 20, right? From the GPIO controller 0. Here I'm not pasting anything in here on the constructor of the GPIO controller, but if you have more than one GPIO bank on your hardware, you can pass this by the GPIO drivers. Okay, we also have here the GPIO drivers inside the system device GPIO. But this is more simple. I am using the GPIO bank 0 and the pin 20 here to show to you guys. So setuping the pin, right? And writing here blink, right? The blink is the hello world of the embedded systems, right? When we receive some kind of board, the first thing that you do or want to do is blink an LED. So let's do a hello world here, blinking our LED. Let's change here to hardware. I already pressed the F5. The F5 is already compiling, doing the making the .NET build for me, and also this will deploy and begin the attach the debugger from the hardware on my Visual Studio Code. And we expect to see the LED blinking, but let's do step by step, right? Okay, let's instantiate the controller. Let's open the pin. Oh, the pin is opened. You can see that when we pin mode output, this is already turned on, or LED. Let's write low. You can see that now we have the LED with the value low. And let's enter onto while. Let's drive the pin to high, turn it on. Let's sleep low. And if I play here, you can see that the LED is blinking. Cool, I'm accessing the hardware without doing any interrupt, right? Behind the scenes, this is making the interrupts for me. The .NET project, the .NET IoT project is doing this. And also I have here on the configurations of my container, right? The Visual Studio Code from extension from Toradex have these features that you can put here, the libraries that your application you use. You can see here that I put here the libgpiod.
It's also
go ahead.
Oh, sorry. It's also important to point out that we are accessing hardware. This is something that usually doesn't happen when you're running in a container, but actually Docker allows you to access the hardware as long as you share it inside the container. So by default, you cannot access it, but you can share something that can be used. And here you can see what we are actually accessing right now.
Yeah, this is important because here I'm accessing only the pin 20 of the GPIO chip 0. So my container only have to access the dev GPIO chip 0. Okay, I'm also sharing here the I2C4 for the next demo, but let's maintain this in this way. Okay, so it's running. Let's go to the next demo because I want to show you guys also because the GPIO access the GPIO is kind of easy. It's the most basic interface on the hardware, right? But let's say that we have a more complex hardware, a more complex device, a more complex peripheral that we want to use and control inside our operation system with the .NET 5. Here we can see on my screen the OLED. I have this mini OLED screen here. This is a very popular OLED screen on the market. And what more we have inside the .NET IoT project? We also have the devices. Let me show here inside the .NET IoT. We have here on the repository inside the source device. And here on the devices, we have the IoT device bindings, right? So each of these folders here are a device, is a peripheral or some sensor, right? So if you have to implement something, maybe you already have it here to use. You can do a new device, a new sensor, and this is ready to use, right? For example, let's go to this place here. Yeah, this one. This is the display that I'm using, right? So if you go through the datasheet of the display, you can see that we have a lot of information to access the right registers, do the right bit assignments, and a lot of things you can see on the datasheet. And this takes time, right? But using the devices here is much more easy. Let me show here. To use this, we have to add the package IoT device bindings. Whoops. IoT device bindings. Let's .NET add. Okay. And with this guy, we have this namespace. IoT device and all the implementations for the sensors and peripherals and other stuff. Cool, right? And I can go through this and do a new and instantiate this and use, right? Let me show here the use of the screen. Let me comment this. I have another demo here for you. This guy here. Oops, demo 2, this one. Okay. So here you can see that I'm using the I2C protocol, right? But I'm also using the device binding for my display, my OLED display module, right? And all the things that I need, all the commands that I need, all the shift registers and bit banging that I need to make this work is already implemented. So as this model of chip of OLED display is a bit generic, I have to make some configuration, right? Because I have the size and other things that also we have on the datasheet, but it's much more easier. Only send the main commands here to the device, right? And do the connection, right? Let's do here step by step again. Let's run this. This will make the .NET build and you publish it and deploy on device. Let's wait, deploying, running, and debugger attached. Okay, so first of all, I have to set up the connection for the I2C, right? You can see here that I'm passing the bus, the I2C bus, because of this bus that I am sharing here inside my container tdev I2C for the I2C4 is the bus that I'm using here, right? And also the address of the device. All the I2Cs have address, okay? So we can connect to device. And with this OLED connection settings, the I2C connection settings, I can use the .NET IoT I2C device create with this OLED connection, and this will make the connection for me. Done, right? And now I can do a new my model here, the OLED display model, passing this device that I created here, and now I can make all the connections, all the commands, and send the data for the OLED, right? It's very easy to use the libraries and the APIs of the .NET IoT. Let's write the hello world on the screen. You can see here it's not, the brightness is not good, but is write hello world there. And also the .NET Conf, and you can see that is running one message by line, right? I don't know if this will focus, but I hope the example.
Yeah, there is also the refresh frequency, it's different.
Yeah.
That's why it's flickering, it's not a hardware issue.
Yeah, it's only on the camera. Yeah, let me, I don't know, to focus you help something here, but yeah, no. Let's, yeah, it's better that this works.
We can. Okay.
So it's it, guys, from my side here.
Okay.
Go ahead.
I think we have some time for the questions. So if you want to,
Yes, Guy. Very good question. Okay, I have some question for you. One is this. Will .NET on Linux IRM means the end of Windows?
I mean, actually, Linux on ARM has been there since quite some time. Probably, I mean, being able to run .NET Core also on ARM devices for some kind of application can mean that people may prefer to run on a Linux device rather than Windows 10 IoT. Windows 10 IoT is still supported. From my point of view, the main issue is that the number of devices that are supported is very small compared to the Linux world. On Linux, you can pretty much take for granted that any new SoC or Wi-Fi chip or whatever is going to be supported. On Windows 10 IoT, the selection is a bit more limited. But yeah, I will turn it the other way around. Having Linux on ARM means that what you write in .NET and maybe run on Windows 10 IoT nowadays may run on Linux in the future.
Okay, and there is another question. Is GPIO controller thread safe? I can control some pin in one thread and the other pin in another thread.
Yeah, you can. But if you are in the same main process, right? You can do it. If you try to use in for example, .NET run once in one and .NET run in another one, so you don't have access to the same GPIO bank.
Okay, I think it's clear. That's all. We don't have another other question. So I thank you guys, and I hope we will see another great session like this.
Okay, thank you very much for everyone attending, and sorry for the glitches at the beginning. It's just my fault. I mean, I follow the guide from Matteo Pagani, so I will share the
Yeah, it's
50%
their
with
fault.
Matteo. But yeah, but at the end it was me doing the session. So okay. But I hope that apart from the glitches and having my frozen camera for some time, all the content was useful.
It's a pleasure to be here. Thank you, guys.
And if you want to play with our extension, just feel free to download it. It's free. And please report any bugs or issues you discover. Thank you.
Thank you, guys.
Thank you very much, Alessio.
Bye.
Thank you, Alessio. Bye-bye.
Bye.
Bye.